Hello again. The last time we were covering this presentation file about simple modeling techniques. As we have mentioned earlier, these simple modeling techniques are helping us to ease the modeling part of complex problems. So these techniques can be applied in many different realistic real-life problems. We have covered a few of them. As you can see, we have mentioned about the additional work requirement in different kind of models. We have said that sometimes the variables cannot be defined in a straightforward manner. In that sense, we need to consider the decision alternatives regarding to our problem, and we need to put an additional work on the model development process. And then we have mentioned about the mathematical relationships between variables. We have said that sometimes a variable can be defined or bounded by the fraction of another variable. These kind of relationships may as well exist between the level of activities or constraints. Usually, our intention would be to create a balance between the activity levels. One way to create this balance was to define an activity or bound it by define an activity as a fraction of another activity, or sometimes we are bounding an activity level by an bound another activity level. So another way of creating balance between the level of activities is to bound the absolute difference between the level of activities, and we have given examples in both of these practices. And actually, the last time we were considering this problem, the manufacturing planning problem here, because our next application is going to be about this manufacturing planning problem. Let's just summarize the information about this question. Remember, now we were manufacturing two parts. These parts are basically sub-assemblies of a finished product. And the profit that we were acquiring from each part was $4 and $5 for each manufactured part. For P1 and P2, we are respectively collecting a $4 and $5 profit per unit. Now, we have said that both of these parts need to go through two processes, drilling and milling. Comparatively, the time that each part spends, either P1 or P2, the time that each part spends in a drilling machine is shorter than the time that they are spending in a milling machine. So each P1 spends 3 minutes in drilling, then 20 minutes in a milling machine. Similarly, each P2 spends 5 minutes in drilling machine and 15 minutes in milling machine. Now, as you can see, the milling machine is creating basically a bottleneck for this problem, for this process. Therefore, the idea here is to use 5 parallel milling machines and single drilling machine. And we have said that our objective is to maintain a balance on loading time on all machines on a single day. Each machine works 8 hours workday, and the total workload that we allocate on the drilling machine or any milling machine should deviate from each other with at most 30 minutes deviation. So either drilling machine can be used at most 30 minutes longer than any milling machine, or any milling it can be used 30 minutes for a duration that is 30 minutes shorter at most. So the time differences between the loads should be less than or equal to 30. So such, and by the way, the question also assumes that the workload on 5 milling machine are equally split among them. Therefore, we do not need to write this constraint between milling machines. However, we need to write this constraint between the drilling machine and any milling machine, because all workloads on the milling machines are equally split between those milling machines. So this constraint was introduced with an absolute value. So basically, we were defining the workload on the milling machine for the production of these parts, and the drilling and milling machine, and the difference between the workloads is calculated in absolute value, and we have put an constraint which bounds this absolute difference by 30. And the final mathematical model was this. As you can see, we have set that our objective is to maximize the total profit for x1 plus 5x2, where x1 and x2 are the number of P1 and P2 produced on a single workday. However, because the workday consists of only 8 hours, and this means 480 minutes, the total load that is allocated on any milling machine and a drilling machine cannot exceed 480. The total load values are calculated by using the time that each milling machine is being used here. And the drilling, as you can see, is the coefficients of 3 and 5 directly, because each P1 requires 3 minutes of drilling time and each P2 requires 5 minutes of drilling time. And for calculating the load on any milling machine, again, we were calculating the required milling time for each part. However, the sum was divided by 5 because there are 5 milling machines, 5 parallel milling machines. So the daily load for a milling machine was 4x1 plus 3x2. So these are bounded by 480 due to the daily workload limitation. And also we have calculated the absolute difference between these two workloads, and this absolute difference is summarized as x1 minus x2 in absolute value, which should be bounded by 30. And we have just learned that if an absolute value function is bounded by an upper bound in the form of a less than or equal constraint, then we can instead write two constraints without the use of any absolute value, and we can say that the content, the inner function in the absolute value, should be less than or equal to 30, while it should also be equal, greater than or equal to minus 30. And obviously, this right-hand side can be positive if we multiply both sides of this inequality with minus 1, which means while x1 and minus 2x2 is less than or equal to 30, 2x2 minus x1, which is the negative counterpart of the same function, should also be less than or equal to 30. So if these two constraints are satisfied simultaneously, this means that the absolute value constraint will also be satisfied. Therefore, instead of writing the absolute value constraint, we can write these two constraints in order to obtain a integer programming formulation here. Finally, the number of parts that we are going to manufacture on any day can only be non-negative integers. And this was the final model that we have seen in this presentation file. Now we are going to move forward, and we are going to talk about the MiniMax and MaxiMin objective functions. Now, here's the thing. There are some situations, some real-life problems where the objective value is to minimize the maximum of many different values. Again, here the objective is to create a balance between the activity levels or decision variables. So let's just say you have multiple activity levels, and what you would like to do is to minimize the maximum of these activity levels. Let's just say you are manufacturing 3 different products, and the quantity that you manufacture are simply x1, x2, and x3. Your objective is to minimize not the summation of them. You are basically trying to minimize the maximum of these 3 values. But you do not know which one is going to be the maximum in the optimum solution. Therefore, such an objective function should be defined as the minimization of the maximum of 3 different variables. A similar situation can also occur as the maximization of the minimum value. So you can say that there are several values that or several activities that we need to perform, but there is the situation at least we need to spend a certain amount of time for the activity which we spare the minimum amount of time. So we do not know for which activity we are going to spend or spare the minimum amount of time. However, we are interested in putting a boundary here so we can maximize the minimum of different values or minimize the maximum of different values. So this minimax or maxi-min situation can be between two or more variables or constraint functions. And in the next practice, we are going to see such a situation. But before that, let's try to understand this concept in mathematical form. So how a minimax objective function is defined. So let's just say, just like in the previous applications, we are defining a sequence of functions gi of the decision variables. Remember now, our decision variables, they constitute a vector x, which is shown in bold notation because it is a vector in n-dimensional real number space. So we are defining a sequence of functions. Each of these functions are converting our decision variables into a scalar value, into a single value in real numbers. And basically, these functions are converting our decision variables into a level of activity. So depending on our choice of the decision variables, and remember now, each of these functions are using the same decision variables, obviously, but each function is defining a different level of activity. Our objective is to minimize the maximum of these activities. So G1 of the decision variables is an activity level, G2 of the same decision variables is another activity level. And our objective is to put a boundary to the maximum of these decision variables. We are basically trying to minimize the maximum of these decision variables. And as you can see, if our objective value is defined as the maximum of this m, activity levels, we can simply say that instead of defining the z as the maximum of these values, we can define z as a value which is greater than or equal to all of these activity levels for a given decision variable assignment. For I changing from 1 to m, we can simply say that z is greater than or equal to all of them. And z is also minimal. We can simply make this definition. So if you simply say z is a variable which is greater than or equal to all of these values, and z is the least possible value satisfying the above inequalities, then basically z is going to be the maximum of these values. So instead of defining z as the maximum of these values, you can also define it like this, or basically we should say that the left-hand side of this statement and the right-hand side of the statement, they are equivalent in definition, okay? Then what we can do is this. Instead of minimizing z itself, which is defined as the maximum of these m different functions defined over the same decision variables, we can simply minimize a single real value z, and we can put constraints which indicate z to be greater than or equal to gi of x. Or by taking the gi of x on the left-hand side, we can simply say z minus gi of x are going to be greater than or equal to 0 for all I. Now, as you can see, the objective function becomes a single value rather than the previous objective function. It is much less complex. and the constraints are going to be z minus gi of x. Now, if these gi functions are simply linear functions, and if you do not do this intervention, then you are going to see that the objective function is going to be nonlinear, because though each of these functions are linear, the maximum of these functions is not going to be linear, because for every assigned value, the maximum can be achieved in different functions. So we are going to see a piecewisely defined linear function, which is going to be convex actually due to the linearity of these functions. However, it is possible that instead of writing our mathematical model like this, we can simply convert it into that one. We can simply say we are trying to minimize a single value, where this single value minus each of the components in this maximum function is going to be greater than or equal to 0. Now, thinking that if these GIs are linear functions, in that case, we are going to have a linear programming model here. Now, a similar situation can also go for the Maxi-Min objective function. However, this time we should be very careful in how we are going to write the statement. Now, let's just say this time our objective value is the maximization of the minimum of a sequence of functions of the same decision variable. Again, our decision variables are constituting a vector of size n, and there are m different functions which are defining activity levels, and our objective is to maximize the minimum of these activity levels. So the least performed activity should be maximized. We do not know which is going to be the least performed, which is going to attain the minimum. However, our objective is to maximize that minimum. Now, as we have said before, instead of defining z as the minimum of these functions, which are defined as a function of the same set of decision variables, we can simply say that z is going to be a value which is less than or equal to all of these functions one by one, and also z is going to be the maximum value which is going to achieve these conditions. Okay, z is going to satisfy those constraints, and z is also going to be the maximum value. Therefore, instead of defining the maximum, instead of maximization of a minimum of several functions, we are basically maximizing a single value z, a single decision variable z, where gi of x minus z is going to be greater than or equal to 0 this time for all functions I. Now, in the next page, we are going to see the same example as before. So we are not going to repeat the explanation, but remember now, we have two parts to manufacture, each of which yields some profit, and each part needs to spend some time in the drilling machine and in one of the 5 milling machines. And again, we are trying to maintain the daily load difference of 30 minutes between all machines, between the drilling machine and any milling machine. And again, we are assuming that a workday consists of 8 hours. So far, what we have mentioned is the same as before. So this means up to this point, the previous model is valid. Now, this time we are going to change the objective function. Okay. Remember now, our previous objective function was to maximize the profit, but this time our objective is not to maximize the profit, but we are trying to maximize the number of completed assemblies per day. Now remember, we are using these parts P1 and P2 to manufacture a single final product. So by using a single P1 and a single P2, we are manufacturing a final product. Therefore, the number of final assemblies, completed assemblies that you are going to manufacture per day will simply be equal to the minimum of these two values. So if, for example, if you manufacture 40 P1 in a single day and 50 P2 in a single day, in the same day, the number of final products, the completed assemblies that you will be manufacturing will be limited by 40, because you only have 40p1 in that case. Now, as you can see, our objective function here is to maximize the minimum of the number of products or number of parts produced on a single day in order to maximize the number of completed assemblies. Therefore, the profit information here for N5 is not important anymore. So even though the table provides them to you right now, they are not important at this point. So what are our decision variables again? Our decision variables are X1 and X2, while X1 represents the number of part 1 to be manufactured on a workday, X2 represents the number of parts of part 2 to be manufactured on the same day. And if we want to manufacture X1 and X2 units on a day, then the number of completed assemblies will be defined as the minimum of X1 and X2 simply, and our objective is to maximize the minimum of X1 and X2. Okay. Now again, X1 and X2 are simply linear functions. The contents, each function here, and they are identified functions also. So they are not complex functions. X1 and X2 are simply variables with a linear function, and the coefficients are simply equal to 1. So this is a simple case, but it would be possible that these, instead of writing two variables here, we may write the functions, different functions of these same variables. But this is simply a simplified case here. And we have to maximize the minimum of these values. Now, both of these values are considered as linear functions. However, when you write the minimum of X1 and X2, unfortunately, the objective function is not going to be considered as a linear function anymore. Okay, it would be a convex function. However, it is not going to conform the properties of being linear. Therefore, we should say that it is going to be a piecewisely linear function, and it is going to be a convex function. Unfortunately, I am very sorry, this is not the case. Let me repeat again. It is not going to be a convex function. It is going to be a concave function this time. Okay, the minimum of two functions is going to be a concave function, but it doesn't matter. Again, the concave function is going to help us to solve this question in an easy manner. Now, how we are going to convert this nonlinear objective function into a linear function and a sequence of additional constraints? Let's just say, by defining z as the minimum of x1 and x2, you are actually saying that z is less than or equal to both x1 and x2. And also z is the maximal value that achieves these two conditions. So instead of writing this objective function in the nonlinear form, we are maximizing z as a variable, and x1 is supposed to be greater than or equal to z, and x2 is supposed to be greater than or equal to z simultaneously, or by taking the decision variables in these inequalities on the left-hand side, we are saying that x1 minus z is greater than or equal to 0, and x2 minus z is also greater than or equal to 0. All right. So the final model is as follows. This time our objective is not to maximize the profit. We are maximizing the number of completed assemblies by the use of part 1 and part 2. And we are defining z as the minimum of the number of parts that are manufactured on the same day. And in order to force this definition on this z, we are introducing two constraints here, where x1 and x2 should be greater than or equal to z simultaneously, because the contents of the minimum function are linear. So this is going to be a linear programming formulation. Again, let me tell you, this is going to be actually an IP formulation, integer programming formulation. Maybe we should add that as well, because the number of final assemblies that you are going to manufacture or the number of parts that you are going to manufacture on that day, all decision variables here are going to be what? They are going to be non-negative. And also, it would be convenient. It would be convenient if you put z itself as a decision variable and in the non-negativity constraint. However, here's the case: z cannot be negative actually in reality because z is defined as the minimum of x1 and x2 according to you, and you are going to say it is maximized here by nature by the enforcement of the objective function here. Z can never be negative. So providing a constraint which indicates z to be greater than or equal to 0 would be simply a redundant constraint.